So this is chapter 12, polyhedrons. Name and describe 5 platonic solids. Platonic solids were solids that had the same shaped face on every side. So one of those would be the square box. If this was a proper looking square, it's not. But it'd be a square box, which, what do we call that? A cube. Or how many sides does it have? 6. And 6 in the Greek language, we usually use the word the letters HEX. So hexahedron. Hexahedron. Okay, we could also use 4 triangles. 4 triangles. So hexahedron is 6 squares. Well, what are we going to use for 4? What word do we use for 4? We talked about this as a video game. Tetris, right? Because it has 4 blocks, right? For each of the little shapes on Tetris, they all are made out of 4 blocks. So that would be a tetrahedron. And that's made out of 4 triangles. What else? We did the one that was an octahedron. That is 8 triangles. We did the dodecahedron, which is 12 pentagons. Kind of looks like a soccer ball. And then we did the icosahedron, which is 20 triangles. That is the 5 that you need to remember. 6 squares, tetrahedron, octahedron, icosahedron. Now, to see what those look like, a tetrahedron, for instance, would have been basically like a triangular pyramid, like this. If you notice, there's 4 sides to that shape. There's the one on the floor, and there's the 3 walls of it. A octahedron, forgive me for trying to draw this, and I'm going to do a horrible job, I'm sure. Okay, that's an octahedron. If you make that with all congruent triangles, they're all equilateral triangles, that's an octahedron. So there's the tetrahedron and the octahedron. I can only pull up a picture of the dodecahedron. There's no way I could draw that. It's going to basically look like a big soccer ball. Now, 1 pentagon is hard enough for me. Trying to draw 12 of them slanted at angles is not going to happen. Okay, Jordan. All right, next question. The net shown at the right may be folded into what 3-dimensional object? So we need to use our names to describe this. Is this object going to be a prism or a pyramid? Is this going to be a prism or a pyramid? Why a pyramid? They're going to fold up into a point, okay. And we could always look at the sides of the shape. If it's a prism-like shape, the sides are probably going to be rectangular. Okay, if it's a prism-like shape, if it is a prism, then the sides will be rectangular. Okay, either they'll be rectangular, or if it's an oblique prism, they will be like parallelograms, but they'll all be 4-sided shapes. If it's a pyramid, when you fold it up, the sides are going to be triangles. So this is a pyramid, but what is the shape of the base of this pyramid? It's a triangle, so this is a triangular pyramid. And what do you call this triangular pyramid if it has all four of those shapes are exactly the same? Well, all of them would be equilateral. And if they were all the same exact shape, they become a, what was the one we just talked about? Platonic solids. What's the name of the one with four? Tetrahedron. Good. If these were all the same shape, if they were all equilateral triangles, then you have tetrahedron, if they're all regular shapes. Okay, number 12C. Find the volume of each of the following. A cube with a 9-inch side. What's the volume formula for a cube? Well, the volume for anything is going to be the area of the base times the height that it stands. Since this is a cube and every side is 9, that means the volume of any, I make these general statements that are just not quite correct, but the volume of any prism-like shape is the area of the base times the height. And the base of this is going to be a square, so the volume is going to be 9 inches times 9 inches for the square. But the height of it is also 9 inches, so that's going to be 9 cubed, which is 729 inches cubed, cubic inches. Okay, so 12D, a cylinder with diameter 6 feet and a height 11 feet. So once again, this is a prism-like shape. When I say prism-like, I just mean that all of the slices are congruent to each other. All the slices are congruent to each other. So we just need to find the area of one slice and multiply it by the height of the shape. So the area of a slice is going to be the area of that circle. And if the diameter is 6 feet and the height is 11 feet, what's the formula for the area of a circle? Yes, it's pi r squared. And what is our radius in this case? If the diameter is 6 foot, then the radius is 3 feet. And the height is 11 feet. Multiply all this out, and I'm going to get 9 times 11, which is 99 pi square feet. Area of the base times height. I put the area of a circle times the height. You could say pi r squared h. That's probably what they're going to have on the formula sheet. But there's no need to memorize formulas whenever you can figure them out. Yes, sir. Thank you. Caught me. That is a square here, and this would be 1, so it's cubed. Remember, this will all be online, so you can go back and re-look at it if you're not caught up. Okay, surface area of each of the following. A rectangular solid that is 14 inches long, 6 inches wide, and 11 inches high. So, a rectangular solid. Let's see, 14 inches long, 6 inches wide, and 11 inches high. Okay, once again, this is just going to be the area of a base times the height. So the volume is equal to, I'm sorry, we're trying to find the surface area, not the volume. Surface area is going to be equal to the sum of all areas. So this means I've got two. The front and the back are going to be the same. They're both going to be 6 times 11. So I'm going to have two 6-inch times 11-inch sides plus two 11 by 14s. If I look at this side, this is an 11 tall by 14 inches. So there's going to be two 11-inch by 14-inch. And then there's going to be two that are going to be 6 inches wide by 14 inches. And once again, this is a formula that you can look up. But guys, not most of your work is not going to be with just simple things that have formulas. So you need to realize that surface area is just the sum of all the areas of the outside, because you can find the areas of the outside. A house is not going to be a perfect rectangular box, but you may have to find the surface area of that house. So multiplying all this out and adding this together, that's going to be 2 times 66, which is, 132 inches squared, plus 28 times 11, that'd be 280 plus 28, so 308 inches squared, and 12 times 14 is going to be 144 plus 24, so 168. Adding those three together, you're going to get 300, 400, 500, 60, 90, 590, 608. Somebody do the math and check me, please. 608 inches squared. All right, good. 12F, a cone with radius of 3 centimeters, a slant height of 7 centimeters, and is missing the base. Nice little catch there, missing the base. We got to make sure we take care of that. Wow, okay, so I must have printed from a different version than I happen to have here. I think I opened this straight from my hard drive and not from the email that they sent me. So this one, let me know if there's any other things that come up that are different. So I'm gonna make sure I change that. It says top. Does that make a difference though? Base of the cone, top of the cone. What's the difference between the base of the cone and the top of the cone? Yeah, so I don't think we can actually take away a point. So I believe, actually, I think missing the base probably made more sense than missing the top does. But either way, so it's missing the circular part. So it's hollow, right? That's what we're talking about. I guess what they're really asking us to do is only find the lateral area of this cone. Only find the lateral area of this cone. Now, this might be difficult for some of us because trying to figure out what the area of that cone is, of the lateral area, without using a formula could be difficult. But do we have a formula for the area of the cone? The surface area of a cone? What's the formula for surface area of a cone? Look in your book. What's the area for surface area of a cone? What's the formula? Don't think it up, look it up. Okay. Now, that is something that actually came up on that. In the book, it takes the formula and then it reduces it. So I only want the thing after the very last equal sign. What's after the last equal sign? So pi r times slant height, L, right? Plus pi r squared. So this is L, the slant height. Okay? And then this is our R. So if I took this is the formula for the surface area of a cone. And if I wanted to take away the top, what would I have to take away? What would I have to subtract from this? What's the area of the top? Pi r squared. So what does that mean for the area of the lateral part of this shape? What's going to happen here? Pi r squared minus pi r squared is going to go away. The formula for the lateral area of the cone. So I'm going to rewrite this. The lateral area of the cone is pi r L, where L is the slant height of that cone. So plugging this in, I know that the radius is 3 centimeters. And the slant height is 7 centimeters. So it looks like I'm going to get 21 pi centimeters squared. Now, we actually derived that formula in class, but it's not as easy. I would not start by trying to derive this formula. Some of the other ones, I think it's really easy to derive them. But this one is not one that's easy to derive. It deals with sectors of circles and sector areas and circumference and all these different things. So I think that it's smarter to start with the formula and think about what we're going to take away. Like in this case, we took away the circle on the top. And that you guys are all looking at me like this was just the easiest thing. So I'm guessing y'all all got this good. So, okay, I'll just move on then. Maybe I'm mistaken. I thought it was kind of a tough one. But let's look at a hexagonal pyramid. Has a height 10 centimeters and a volume 578 centimeters cubed. Find the approximate volume with a similar pyramid with a height of 6 centimeters. Okay, this brings us back to our similar figures problems. And you were not with me last hour whenever we went over chapter 11, but we talked about that's a 6-inch pizza. How many 6-inch pizzas do you need to buy to replace one 12-inch pizza? How many 6-inch pizzas do you need to buy to replace two 12-inch or to replace one 12-inch pizza?
4, 3, 2.
Let me ask you this. Does this change your opinion?
4. Yeah, you cut it up.
Would two 6-inch pizzas fit across this 12-inch pizza? It's 6 inches plus 6 inches is? So this should be 6 inches and that's 6 inches, and you've got 12 inches across. Did they cover the entire 12-inch pizza? It don't matter if you cut them up or not. They're all sitting on top of that pizza, and there's more pizza on that 12-inch pizza. It takes 4 of these to equal 1 of those. It's 4 of them. Let's just do the math. R here is 3. So this is going to be 3 inches squared pi. R here is 6. And then we come back and we say, look, this is going to be 9 pi inches squared. This is going to be 36 pi inches squared. How many 9s does it take to get to 36? 9 times 4. Okay, this is the concept of similar objects that we talked about back when we did area and back when we did volume. It is not, doubling the size of an object does not double its area. It does not double its volume. It's more than that. If you double the size of a pizza from 6-inch pizza to 12-inch pizza, you multiplied its area by 4. If you go from a 40-inch TV to an 80-inch TV, you just got 4 times the size. It takes 4 40-inch TVs to fit inside the same space as one 80-inch TV. So, and that's only talking about area. When we get to volume, it's actually going to be cubed. So what happens is, if this is double, if this is going to go 6 times 2 to get to 12, then the area is going to have to be times 2 squared to get to the new area. And the volume is going to have to be times 2 cubed to get to the new volume. How many of you guys remember us talking about this? Do you remember talking about digging a hole? I had a problem about if you dig a hole and the old lady asks you to dig one twice as deep, how much are you going to charge her? Man, I'm going to take you to the bank every day. You're going to make me lots of money. I'm going to ask you to dig me a hole twice as deep, and you're going to be there for 8 times as long. But you only charge me double. You see what I mean? Because it's twice as deep, twice as wide, twice as long. That's twice times twice times twice, which is 2 times 2 times 2 is 8. That's why it's 8 times as much work. Just like here, it is twice as wide, but it's also twice as tall. So it's 2 times wide and 2 times tall. It's 4 times as much. Why am I bringing all this up? Because now we're about to do a similar pyramid. And these are not the most difficult, but you have to remember this times 1, times 2, or times 3. Sorry, I shouldn't say times 1. To the first power, the second power, or the third power. Let's look at this. Let's look at the heights. What is the ratio of the 2 pyramids? What's the bigger pyramid's height? So height of the large one is equal to 10 centimeters. What's the height of the small one? So what's the ratio of the large to small? Right, you could reduce it, right? You could reduce it. So you're going to put okay, 5 over 3, and it's going to reduce to that you don't have to have the centimeters there. So the ratio would be 5/3 for the length of the sides. 5 to 3. What about the volumes? What about the surface areas? Okay, so let's take a look at that. If I'm talking about surface area, this is going to be, the bigger one is 5/3 the smaller one. Now, we're not just using doubling anymore. We're using something like a fraction like 5/3. So the bigger one is 5/3 the smaller one. What should we do to get the area? The area of the large one and the area of the small one. So the area of the large one is going to equal to 5/3 squared. the area of the small one. This is our scale factor. And the volume of the large one is going to be equal to 5/3 cubed the volume of the small one. Okay. My easy way to remember this is I think of how many dimensions it's in. If I'm just measuring height, how many directions do I measure? First dimension, one direction, first power. If I measure area of this floor, how many directions do I need to measure? What's the area of this floor? What's the formula for it? Length times width. So that's how many directions? 2. So that means 2 dimensions. We're measuring in 2 directions, 2 dimensions. That's why it's squared. And volume of this room would be the length of the floor times the width of the floor times the height of the room, which is how many directions? 3. So you need a cube to get to the answer. So now we can forget all the rest of this. We've got our formula. Our formula is that the volume of the large one should be equal to 5/3 cubed the volume of the small one. So now, which one did they give us? They gave us the volume of the large one, right? So we need to just plug it in here. Okay. You can go ahead and cube 5/3. 5/3 times 5/3 times 5/3. Just remember the cube goes to the top and to the bottom. What's 5 cubed? 5 times 5 times 5? 5 times 5 is? Times 5 is? 125. What's 3 times 3? Times 3? 27. Okay, how do I get rid of a fraction? If I want to get that fraction gone from VS, what do I do? Multiply by the bottom, or I could multiply by the reciprocal. If I want to do it in one step, I can multiply by the reciprocal. But let's start by just multiplying by the bottom. Oh, I did that earlier. That wasn't good. I did. Okay, 27 times 578 centimeters cubed. Okay, the 27 and the 27 are going to go away. And whatever this is going to end up being, 27 times 578 centimeters cubed. Now, how do I get rid of the top, 125? This is 125 times VS. How do I get rid of that? Divide by 125. What's 125 over 125? Reduces to 1. Put that into your calculator and tell me how much the volume of the small should be. 27 times 578 divided by 125. Anybody got it in the calculator? Just tell me what it is. Anybody corroborate that? 27 times 578 divided by 125. Anybody got that? Somebody double check that. All right, we're going to go with it if nobody's going to double check it. Good? Okay, it was right. I didn't hear you guys say that. Okay. 12H. If a cylinder intersects a plane perpendicular to its base, what is the resulting cross-section? Okay, what's the base of this shape? Circle. what direction would a plane be going if it was going to intersect perpendicular to this base? Up and down. So if a plane came in, and I'm not talking about like, you know, American Airlines here, talking about geometry plane, right? So if a plane intersected this circle, what shape would it create? What shape would that be? It does look like a parallelogram, right? Because I'm cutting it in 3D. But let's take something a little more realistic. Now, this isn't a cylinder, but it's close. If I was to cut this, hope it doesn't leak. If I was to cut this way, what shape, after I remove the outside, what shape would you see? A rectangle. Yes, in 3D drawings, that's going to look like a parallelogram, but it's actually a rectangle. That's a rectangle. So the answer is a rectangle. Okay, if a hexagonal prism intersects a plane parallel to its base, what is the resulting cross-section? Hexagonal prism. What did we say we know about a prism type shape? That's a hexagon on it's like 3D hexagon. It looks horrible. You're right. But what do we know about what do we know about prisms? We talked about prisms when we were in chapter 12. Parallel bases, and what are the sides made out of? Rectangles. Okay? And the one thing I told you that sets prism-like objects apart is that every layer of this prism is going to be congruent to every other layer of this prism. So, if a hexagonal plane intersects hexagonal prism intersects a plane parallel to its base. So if this plane were to slice through that prism, if it's to slice through that prism, what shape would I get back? Hexagon, same as the base, yeah. It's like a big block of cheese, right? If I just slice off a layer using this knife, the layer is going to look like a hexagon. All right. Now, you guys remember this one? This was, we learned it first way back like in 8th grade, doing the pictures from each side. So you remember the left view, the front view, and the top view? So if I look from the top, we'll do the top first. What shape do I see from the top? Well, I definitely see that shape right there. But I also still see these two blocks right here. Even though they're set below, one of them goes there and the other one goes there. This is the shape I see from the top. So what do I see from the front? Sorry, I should say this is right. What do I see from the front? Well, call that front. How many blocks do I see when I'm looking from this direction? 1, 2, 3, 4, 5, 6. That is what I see from the front. Finally, what do I see from the right? I see this block, this block, this block, this block, this block. Oh, I think let's see. Let's do that. Yeah, okay, so you got isometric and you got orthographic. So whichever one it's in, if you don't want to have to worry about memorizing the words, whichever one it's in, convert it to the other. Okay. And that's the end of that section. Oh, that's what I'm looking for.